Our third example here, the ideal Brayton refrigeration cycle. Okay, so this cycle, as you can see in our PowerPoint document that we loaded, consists of actually, instead of throttling valve, we have a turbine driving the compressor, and we have two heat exchangers here. This is a heat exchanger, and this is another heat exchanger. So what we have here is a compressor, a turbine, so this system we have. Okay, so here we have state 1 and state 2, state 3, and state 4, okay, going in this direction. Now we have therefore Q dot in here. So this is this heat exchanger can be evaporator, this heat exchanger can be condenser, okay, for the vapor refrigeration system. So this is the gas refrigeration system. So this is the main difference. So the working fluid here can be air. And if you look at the TS diagram for this, so we don't have the two-phase system. So we have here a typical gas. So we have the state 1, state 2, state 3, and state 4. Okay, so please take a look at your notes. It is used, this system is used for also the refrigeration. And here, our example, this is our example. We have an ideal Brayton refrigeration cycle, and air is the working fluid. So it enters the compressor of an ideal Brayton refrigeration cycle at 100 kilopascal and 300 Kelvin. Okay, 100 kilopascal and 300 Kelvin. The compressor pressure ratio is 3.75, and the temperature at the turbine inlet is 350 Kelvin. So let me just put the numbers. Actually, T1 here is 270 Kelvin. Okay, so this is P2 over P1 is 3, the ratio, and T3 here is 310 Kelvin, and we have a 100 kilopascal. Okay, so I just changed the numbers, and so we have from 1 to 4 100 kilopascal here, and we have 300 kilopascal here. So this is 270 and this is 310 Kelvin. So this is TS diagram. So these are the data, and we are asked to calculate the network, the refrigeration capacity, the coefficient of performance, and also what is the coefficient of performance of a Carnot refrigeration cycle operating between the same reservoirs. Okay, so here what is the states? State 1 is T1 is 270. Now this is an ideal gas, so use ideal gas tables, ideal gas air tables. So directly we go there and 270.11 kilojoule per kilogram with a PR1 of 0.959. So for state 2, what we know the pressure ratio. Okay, so here pressure ratio is known. So for that, PR2 is equal to PR1, P2 over P1, which is 2.877. Okay, so this ratio is actually 3. So this is 0.959. So this is 2.877. So with this information, we can look up the table, and this is kilojoule per kilogram. So for state 3, what do we know? State 3, we know the temperature. So temperature is 310 Kelvin. So H3 is kilojoule per kilogram, and PR3 is 155.46. So for state 4, we know the ratio again, PR4, PR3, P4 over P3. Okay, so P4 over P3. So this ratio is 0.5182, and H4 is then 22625. So with this information, the net work is V dot cycle over M dot, which is of course compressor minus turbine network divided by flow rate, H2 minus H1 minus H3 minus H4, okay, in terms of kilojoule per kilogram. So with all the information, we get 16 kilojoule per kilogram. So this is V dot cycle over M dot. So the refrigerating capacity is actually Q dot in per M dot, which is H1 minus H4, and this is 270.11, 226.25, 43.86 kilojoule per kilogram. And the coefficient of performance, which is beta Q dot in over M dot divided by V dot cycle over M dot, which is 2.74. And if you look at for the ideal, okay, the coefficient of performance for a Carnot refrigeration cycle operating between the same for reversible cycle, T cold 270 Kelvin and T hot. So when you compare that, beta max, the maximum this system can perform is 270, which is 6.75. So it is well underperforming, but of course this is a fully reversible cycle. So this is very similar to the gas power cycles, but it can also be used for refrigeration system.